Okay, so here we go. So let's talk a little bit about the combined gas law. So I have it there on the screen, and so the thing that you'll notice is kind of similar to previous gas laws, but a little different. So the way it's similar to previous gas laws is what we used to do is we would have a gas at some kind of initial condition, say we'll call it condition 1, and then we were relating to it the gas at new conditions, we'll say condition 2. So that is still there when we see this combined gas law. But here in the combined gas law, instead of seeing two variables being related to one another, now we're seeing three variables. And so those three variables are pressure, volume, and temperature of a gas. So we can relate those three variables at a new condition from the gas at the original condition, as long as we understand that that gas is not changing its number of moles as you're going from that original condition, condition 1, to the new conditions, condition 2. So one thing to notice about this law is basically it's a fusion of some of the earlier laws we were looking at that had two variables in them. So one thing you can see in there in that law is that there is Boyle's law in there, which is P1 V1 equals P2 V2. Superimposed on that is Charles' law, which is V1 over T1 equals V2 over T2. And then Adamanton's law, which is P1 over T1 is equal to P2 over T2. So when they're all fused together, it gives you the combined gas law. And so one thing you'll have to do when using this gas law is if you have a temperature in something other than Kelvin, you will have to convert it to Kelvin. So most of the time in these problems you'll have a temperature in Celsius, and so if that is the case, then just add 273.15 degrees to get it into Kelvin. Probably the best thing to do is for me to try a problem like this on the board, and I'll give you some tips to solving this. Okay, so we have a gas that occupies 10 liters at 240 degrees Celsius under a pressure of 80 kilopascals. At what temperature will the gas occupy when it's at 20 liters if the pressure is increased to 107 kilopascals? And so looking at this problem, what we can see is that we have three pieces of information, three properties, which are the volume, the temperature, and the pressure of the gas. And so let's see if we can define some initial conditions and then see what we need to solve for in the new conditions. So the volume initially is 10.0 liters for this gas. The temperature is 240 degrees Celsius, and so I'll have to convert that to Kelvin in just a second. The pressure is 80.0 kilopascals. Okay, so let's see how we can define the variables in the new conditions that we're going to bring this gas to. It says at what temperature? So it looks like we're trying to find T2. So that is the unknown in this problem. Let's see, we have a new pressure, P2, which is 107 kilopascals. And then we have a new volume, V2, which is 20.0 liters. Okay, so we're trying to find T2. So I think what I'm first going to do before I derive the appropriate equation that we can plug in numbers to is just first, let's just take this initial temperature at Celsius and convert it to Kelvin, sort of like as I was doing it before. So what you do is you add 273.15, and kind of like I pointed out before, we'll get a calculator answer, which is 240 plus 273.15. So the calculator answer I get is 513.15. But I think at this point, what I want to do is solve this problem in the way that the book does it. And what the book does is when you have a temperature, the first thing you do is get that into the correct number of significant figures, and then once that's done, plug it into the equation and then solve. So we have 240, and there's a decimal here, so the uncertain digit in 240 here is in the ones place, so this has three significant figures. The uncertain digit here in 273.15 is in the hundredth place, and so there are five significant figures here. And so again, the calculator answer will be 513.15, but you might recall the rules for adding numbers for significant figures. And so here, the number we should get should be rounded to 513, with its uncertain digit in the ones place. Okay, so this will be in Kelvin, so I'll put a K here. Okay, so the next step is to go ahead and solve this equation for T2. So let's see if I can do that. So it's going to be P1 V1 over T1 is equal to P2 V2 over T2. So this can be a little tricky deriving these equations for the variable you want to solve for, but what I'm going to do is I'm going to take T2, which is the denominator here on this side of the equal sign. If I want it in the numerator, I have to put it on the other side of the equal sign, so it goes up here like this. And so what we can do is write that out, see what we got now. So we have T2 P1 V1 over T1 is equal to P2 V2. And so the next step is we got to move out the other variables so that T2 is by itself. And so we're going to move P1 V1 from this side of the equal sign, and it will go into the denominator. It goes to the other side of the equal sign. And T1 here, we have to move out as well, and it goes to the other side of the equal sign. It will go in the numerator like that. And so what I get is T2 is equal to P2 V2 T1 over P1 V1. So I think that's correct. Okay, so let me just go ahead and plug in some numbers and just confirm that the units cancel as expected. So P2 is 107 kilopascals, and V2 is 20.0 liters. And we also have T1, which is here. It's going to be 513 Kelvin. And then over P1, which is 80.0 kilopascals. And then we have, it looks like V1, which is 10.0 liters. So let me see what number I get here when I get this. And so I get 107 times 20 times 513 divided by 80 divided by 10. So the number I get on my calculator is 1372.275. The book again suggests that at this point, after you plug the numbers into the equation, you get a number from the equation. You should round this to the correct number of significant figures at this point. So it looks like, if you check carefully, this number needs to be rounded to 3 significant figures. So here are 3 here. Here's the uncertain digit. We'll look to the right of that. It's below 5, so we do not round up. So what I get is 1370, with this 7 being the uncertain digit. This 0 is not significant. And so remember, this is in Kelvin. So the final step is, I think the problem is asking, well, what temperature it should be. Now, it doesn't say it has to be in Celsius, but let's just calculate into Celsius. So it's minus 273.15, and let's see what we get. So I get 1370 minus 273.15, and so I get 1096.85 on my calculator. But again, we have a significant figure furthest to the left here, and this number here compared to this, uncertain digit here, and compared to this uncertain digit here. And so we have to round such that the answer has an uncertain digit here in the tens place. And so we look to the number next to it, and it's above a 5, so we round up. So this rounds up to a 0, and this next digit becomes 1. So I get 1100 degrees Celsius, with this 0 being the uncertain digit. So this has 3 significant figures. So if you wanted to, you could write this as 1.10 times 10 to the 123 degrees Celsius. And I think that's the answer I got on the screen. It is. Okay, so we will move on. Okay, so the next problem I'm just going to point out, I'm not going to solve it, but I encourage you to try this problem on your own. And so you use the combined gas law to solve this problem, which is P1 V1 over T1 equals P2 V2 over T2. So I encourage you to stop the video for a moment and just try that on your own.